Welcome. Today, we will delve into the critical process of electrolyte filling in battery manufacturing. This step is fundamental to achieving optimal battery performance and reliability. We will explore the methods used and the factors that influence success. Electrolyte filling is a crucial final step in battery assembly. It involves introducing the liquid electrolyte into the cell, saturating the porous electrodes and separator. This process is vital for enabling ionic conductivity, which is essential for the battery's electrochemical function. Mastering electrolyte filling involves several core steps. These include preheating the cell, precise electrolyte injection, applying vacuum and pressure cycles, and allowing for adequate soaking duration. Each step plays a vital role in ensuring uniform wetting and optimal performance. The process begins with initial cell weight verification to establish a baseline. Precision electrolyte injection follows, ensuring the correct amount is dispensed. Multi-stage vacuum and pressure cycles are then applied to facilitate penetration and remove gases. Finally, a final weight confirmation verifies the electrolyte uptake. Preheating the battery cell before filling is essential. Raising the cell temperature reduces electrolyte viscosity, significantly improving its ability to wet the electrode pores. This thermal conditioning also helps remove residual moisture and gases, preparing the cell for efficient filling. Precise electrolyte injection is critical. The exact volume or mass of electrolyte must be determined based on electrode porosity and cell design. Using high-precision dosing methods, often gravimetric, ensures the correct stoichiometric balance for optimal electrochemical reactions and consistent cell performance. Electrode structures, especially in high-energy density cells, can be highly compacted with narrow, tortuous pores. Vacuum and pressure cycles are employed to overcome these challenges. They are designed to ensure the electrolyte penetrates deeply into every part of the electrode structure. Vacuum cycles work by evacuating air and gases from the cell's internal structure, creating a pressure differential that draws electrolyte in. Pressure cycles then actively push the electrolyte deeper into the pores. These alternating cycles are often repeated to maximize wetting and gas removal. The vacuum method involves placing cells in a chamber and evacuating it to a high vacuum level. Electrolyte is then introduced while maintaining this vacuum. The pressure differential pulls the electrolyte into the porous structure. A vacuum hold time allows for deeper penetration and gas escape. Key parameters for the vacuum method include the vacuum level, evacuation time, and vacuum hold time. The principle relies on creating a low-pressure environment that effectively draws out entrapped gases and pulls the electrolyte into the intricate pore network of the electrodes and separator. The pressure method utilizes positive pressure, often applied using gases like nitrogen, to force the electrolyte into the cell. This method can be efficient, particularly for high-volume production. Electrolyte is introduced under controlled pressure, pushing it into the electrode pores. Parameters for the pressure method include the applied pressure, filling rate, and pressure hold time. While higher pressure can speed up filling, careful control is needed to prevent gas entrapment. Filling is typically performed in a dry room to maintain electrolyte purity. After initial filling and cycling, a sufficient soaking duration is necessary. This allows the electrolyte to fully permeate the electrode structure, ensuring complete wetting of all active material surfaces. It facilitates optimal electrolyte distribution and interfacial contact. Insufficient soaking leads to non-uniform wetting, increasing internal resistance and reducing capacity. Key parameters include the duration and temperature of the soaking period. Elevated temperatures can sometimes accelerate the wetting process, but must be carefully controlled. Minimizing gas entrapment is crucial. Trapped gases reduce the active surface area for reactions, increase resistance, and can cause cell swelling or localized hot spots, compromising performance and safety. Effective filling methods and post-filling steps are vital. Quality control is paramount. Methods include weight checks after filling to confirm uptake, visual inspection for defects, and impedance measurements to assess internal resistance. Advanced techniques like X-ray or CT scanning can verify wetting uniformity and gas presence. Electrolyte filling is a cornerstone process impacting battery life, performance, capacity, and safety. Success hinges on proper preheating, accurate dosing, optimized vacuum/pressure cycles, and adequate soaking. Ongoing advancements continue to refine these techniques for future battery generations. That's it for now. Thank you.